Right. Hello. I am Miguel, part of Ozbay's class for 2025 of the summer semester, and this is Project 3, Part 2, where we will be doing a laminar flow over a cylinder. Um, in the previous video, in the previous part, we've done the mesh. We will be reusing that mesh throughout for the laminar simulation and the turbulent simulation. So yes, yep. Now go Fluent, share it with the mesh here, and all we gotta do is just set it up. Click here, double precision, and 6 processes. Yep. Okay, we're here. It did the same thing again as before. Um, we just need to change the surface from a solid to a fluid. So we could just change it here. And there you go. Problem fixed. Alright. For a model, we will be doing a laminar simulation. There you go. Reference values, this will be important. Um, this will be computed from the inlet. I'm not going to do this just yet. I'll be doing this after I put inlet conditions. So go in the inlet conditions. Now for this simulation, we need to choose a Reynolds number to ensure that the flow around the cylinder is laminar. I will be going with 150. Reynolds number is very low. This is just to make complete certain that it is truly laminar. So there we go. So 150, and to calculate velocity, it would be your Reynolds number times viscosity divided by your density times your diameter of the cylinder. So it's 150. The viscosity by default answers would be 1.7894 power of -5 and 1.225, and then we multiply that by 1. This is a 1 meter diameter, and we get 2.1911 times 10 to the -3, basically. So 2.911 over 0.00. There you go. That is our velocity. And then now we could compute from inlet. I did the boundary condition first before putting in compute from inlet, because if I were to do it afterwards, it would not just automatically plug in my number. So yeah, this is a little bit more efficient like that. Make sure this is all good. So okay, yep, it's all right. We're done with that. Then going down, report definitions, new force support, drag coefficient along the cylinder, and print console. Go. monitor, edit 1e -6. Go. And then now we will be good to initialize. For initialization, I'll just go a little bit more, a little bit extra here, and initialize. Go. It's good. All right. Number of iterations, I'll put 1000. It will likely cut short of that, so now we could calculate. All right. Our simulation is done, and now we could post-process our results. There you go. Of course, you could right-click and compute your drag coefficient, and then, like before, you could just open up our contours. pressure. Okay, so there you go. Looks good. Now velocity looks pretty good as well. Now, if I were to go back, I would probably increase the domain along the side if you really want to capture more of the wake. Um, but that won't really be necessary because our goal will be just the plots, observing them, and of course our plots here, the pressure coefficient and the velocity over the surface. So here we're going to do pressure coefficient along the cylinder. There we go. Looks pretty reasonable. And do a new one, and this will be velocity over the surface. And it's 0. This is to be expected. In the previous case, it was an inviscous flow, meaning that there's no viscosity on the fluid. This case, however, we're doing a laminar flow, and it is viscous. With a viscous fluid, especially in well, it's not entirely true in real life, in reality, in simulations. We always assume that in a viscous fluid, on the surface, the velocity of the fluid will be 0 relative to the object in question. Um, this is because of viscous forces acting on the surface, and yeah, essentially you would have molecules pretty much stuck on the surface of the object. That's why you have a velocity of 0, and this will be to expected in the turbulence model as well. There you go. So yeah. Now go here, and let's do our velocity streamlines. Stream function. There we go. Oh, stream function. But this is also a good plot actually. This will just this is not stream function, but rather the magnitude. So just cut it into lines, and you could also observe it like this, which is very nice. So there we go. But we're interested in stream function, and it behaves like that. There you go. And it looks pretty reasonable. You can see the flow kind of circulating in on itself. The mesh in here is a little bit off. That's all right. If you want more accurate results, you need a finer mesh. So yeah, this looks good. And that is the end of case 2 of laminar flow.